ratio, so they're not getting lots of lift from that. They don't fly very fast. Instead, they have a very high camber to their wings. And so they're slower moving birds with high camber. Camber gives them that extra lift that they need. There may be some slotting in the primaries as well, but not always. So these are adapted for slow speed and maneuverability. That's the kind of wing you're going to find in your typical dickey birds living in the forest. Right? It's a catch-all wing. It doesn't allow you to move at extremely high speeds. It doesn't give you the greatest amount of lift possible, but it's this big compromise between lift and maneuverability. Lift, speed, and maneuverability. And that's what most birds are, most Passeriformes. They are that compromised bird. Even anything that, like a pheasant or a chicken, is going to have that kind of a wing. They're not adapted for high speed at all. So these are just the 4 standard wing forms in birds. You can take a bird that you've never seen before and sort of guess at its foraging tactics by simply looking at the shape of that wing. You can tell whether it should be able to move fast or whether it's a bird of open areas that is relying upon soaring, or is it an animal that relies on static soaring, okay, just by looking at that wing. Questions? Okay.
Oh, wait, I did have one. So then an owl, would they be under the slotted soaring description, or would they be more elliptical?
I think this is going to be more elliptical in the long run.
Okay.
Yeah. Because they have to be fairly maneuverable in order to hunt in the areas that they hunt. And there would be variation, I imagine, among the different owl species too. All right. Okay, let's do start on mammals a little bit. Anybody in mammalogy can leave the room if they want, since they've already heard all of it. Okay. Well, mammals evolved from reptiles. And if we go back in time to the Mesozoic era, what you'll find that most mammals at that time were small. Right? Look at the fossils. 20 to 30 grams is a typical size of a mammal back during the Mesozoic era. Right? 20 to 30 grams is the size of a small mouse. Right? We're not really large animals. The Mesozoic era is known as the age of reptiles. And that's because it was dominated by the dinosaurs. Dinosaurs were exceedingly abundant. They were very, very large animals, many of them. Not all, but many of them. What occurred, though, once we got out of the Mesozoic and into the Cenozoic, is that we get a huge increase in diversification of mammals. Go with so this is the handouts in your pack. But it's just a graph that is illustrating an increase in diversity of mammals. So they're using as their metric for diversity the number of different genera that were known of mammals. And you can see this over in here then is going to be your time, the Mesozoic era, that is dominated by the reptiles. And then you get into the Cenozoic era, and you can see that we're getting a huge increase in diversification of the mammals. For a long, long period of time, there just simply were not very many mammals, and then it took off. Right? So the Jurassic, Cretaceous, those are subdivisions of the Mesozoic. As you get into the Cenozoic era, we have other subdivisions, the Paleocene, the Eocene, etc. All right. Huge increase in diversification of mammals. Why? Well, it corresponds to 4 different things, 3 biological trends and 1 geologic trend that was occurring at approximately the same time as this transition from the Mesozoic to the Cenozoic. What are those trends? Well, first off, how do you spell disappearance? Disappearance of the dinosaurs. So we did talk about that a little bit, and there's a lot of speculation that the dinosaurs died off, particularly all the big ones, because of a meteor that came down and the ultimate effects of that meteor. But nevertheless, these large animals that dominated the earth were no longer there. At the same time, we get a diversification or a spread of angiosperms. What are angiosperms? Flowering plants. Okay? All right, so we suddenly have this new material out there that's potential food, right? Potential resource for the mammals, suddenly becoming more common. We've also had an adaptive radiation of insects. Okay, adaptive radiation of insects into pollinator and herbivore niches. Okay, so the insects are taking advantage of the fact that now, all of a sudden, we got all of these angiosperms that were never there before. All right? Angiosperms have to be pollinated, and so we're getting a diversification of insects that are becoming pollinators, different kinds and greater numbers of them. And at the same time, we got all of these new plants. The insects are going, woo-hoo, this is new food, let's go for it. And so you're having the spread of angiosperms concomitant with an adaptive radiation of insects going on at the same time that the dinosaurs are disappearing. And the geologic thing that was occurring is the breakup of the continents. So you have continental drift occurring. Continental drift leads to isolation. Isolation can allow then 2 groups of animals to go through anagenesis separately and ultimately give you 2 different species. So all of these things combined were going on at this time here and favored that huge increase in the diversity of mammals. Here, you lost a major predator and competitor, but a major predator, because most of these guys were big and you were a little tiny thing. You weren't going to ever evolve to be a big mammal because you'd get eaten by the big dinosaur. So we got rid of potential predators, potential competitors. We have new niches because of the angiosperms. New niches because of the adaptive radiation of the insects. Many of the first mammals were believed to be insectivorous. And then finally, we had geological factors that favored speciation, the development of new groups of animals. Okay, so we did come from the reptiles. There's an excellent fossil record. It's probably one of the better fossil sequences that is out there. The transition from a reptile to a mammal is very, very well documented in the literature. Well, let's look at some mammalian traits then. Some of these things they share with birds. Endotherms and homeotherms. What's an endotherm?
An animal that has a higher metabolism, so it generates heat from itself rather than relying on like bathing in a sunny environment.
Okay. I probably should have defined this one first, but a homeotherm then is an animal that is going to maintain a constant body temperature, usually at some distance above the ambient. And what an endotherm is telling you is where is the source, what is the source of the heat that is being used to maintain that higher constant temperature. An endotherm uses internal physiological reactions to produce that heat, as opposed to something like a lizard that is an ectotherm. A lizard during the day can be fairly homeothermic and keep its body temperature up around 35, 40 degrees centigrade for hours. But the source of the heat is typically the sun. The animal basks in the sun and keeps its body warm that way. Mammals, though, and birds are endotherms. They produce their own heat in order to keep that body temperature up. Let's see. Circulatory system. We have a complete double pump circulatory system. What does that mean? Well, let's go back to fish, because we're at two ends of the spectrum. In a fish, low oxygen blood comes into the heart. It is pumped to the gills for oxygen. Then it goes to the body to deliver that oxygen. The heart develops pressure to move the blood out, but almost immediately, most of that pressure is dissipated by the friction in the capillaries of the gills. So when the blood high in oxygen comes out of the gills, it's at very low pressure. What birds and mammals have is a complete double pump system. So we use one side of the heart to pump the blood to the lungs. That pressure is dissipated in the capillaries in the lungs because of the friction. But instead of then going to the tissues, it comes back to the heart, the other side, the left side, and then it is pumped out to all of the tissues of the body. Because you have a double pump system, the blood high in oxygen can go to your tissues at a much higher pressure. That means that you can deliver more oxygen per minute to your tissues if you have the double pump system than if you have the single pump system. Why is that important? Because you're maintaining this very high body temperature using internal physiological reactions. You need lots of oxygen in order to do that. So you need some adaptations that are going to allow you then to deliver oxygen to your tissues so that it can help fuel all of those reactions that are going to keep that body temperature high, as well as do anything else that you need to get done. Going along with it, there's the adaptation in the lungs. So if you look at the terminal part of lungs in a mammal compared to any other vertebrate, this would be the terminal part. It looks like a cluster of grapes. Use your imagination. Looks like a cluster of grapes, right? Those are hollow little sacs. Each one is an alveolus, plural alveoli. That is how mammals get a huge surface area to their lungs, by all of these internal subdivisions into many tiny alveoli. The internal surface area of the lung of a mammal vastly exceeds the internal surface area of any other vertebrate. Why is that good? You get your oxygen across the surface area of your lungs. The more surface area you have, the more oxygen per minute you can obtain. That helps you fuel, maintaining that high, constant body temperature and everything else that